it should work. Share. Okay.
Okay, it's working.
Let me go to.
So please try to recover a little bit of the 10 minutes delay.
Okay, we'll try. Okay,
Thank
good.
you.
So I'm going to talk about bottomonium properties at high temperature from lattice NRQCD. And that, of course, goes related to what Mike's talking about, but from different perspective, from the perspective of lattice calculation. So the work I'm going to talk about is based on the papers I wrote with Rasmus Rausen, Stefan Meinl, Swagato Mukherjee, and myself. And just remind you, Mike already talked about, I don't have to explain too much, but essentially the in-medium properties of bottomonia or any other mesons at high temperature are encoded in the spectral function, which is related to the retarded correlation function of two meson currents. And of course, what we calculate on the lattice is a current correlator, but now in Euclidean time. What we know essentially from analyticity is that the Euclidean time correlation function is related to the real time correlation function. Therefore, you could represent your Euclidean correlation function in terms of the spectral function and through the integral transformation, which is based on this finite temperature kernel. And then, of course, a lot of effort was going on in the past 20 years, try to invert this integral transformation, and from given the lattice result on the correlation function, get some estimate of the spectral function, which then should encode the quarkonium properties, in particular bottomonium. Okay. Now I will be talking about lattice calculation in using non-relativistic QCD on the lattice, and here, of course, I want to remind what is non-relativistic QCD. So we know that quarkonium, to a good approximation, are non-relativistic, which means that the momenta are much smaller than the mass, and therefore we could integrate out the physics at the energy scale of the heavy quark mass and derive an effective theory which just describes the physics of the order of the heavy quark momenta, which are much smaller. And when doing so, we get a field theory where we have a non-relativistic Pauli spinors, psi and chi, describing the quark and anti-quark, and the light degrees of freedom. The light quarks and gluons remain intact, but now they're at lower energy scale. Now, that has, of course, a lot of advantages, because now the large quark mass of the bottom quark doesn't enter the calculation, so we don't have this large scale, and therefore we don't have to worry about lattice artifacts, which in usual lattice calculation would scale like the lattice spacing 8 times the heavy quark mass. And of course, in today's lattice calculation makes this product much smaller than 1 is challenging. But if you don't have these mass scales, then you don't have to worry about. Now, the spectral function is less dominant by the high energy modes. So that, of course, also good, because you have now more sensitivity to the bound state properties when you try to reconstruct the spectral function. And there is one added bonus, that now, because you don't, you integrated out the heavy quark mass, you don't actually thermalize bottomonium completely with the medium. So they're actually to some extent external probe. And that means that the integral transformation that relates your Euclidean correlation function to the spectral function actually simplified. So instead of this periodic Koch form, you have a pure exponential decay, and therefore you have a larger time extent, which is now still limited by inverse of the temperature, but it's a factor of 2 larger than in the usual relativistic formulation. So that's another thing to keep in mind. So now we put this effective theory in the lattice. The lattice, of course, provides a natural UV cutoff for this effective theory, but now we have to keep in mind that the inverse lattice spacing should be smaller than twice the quark mass. In other words, the lattices that we use in this calculation cannot be too fine. So they have to be actually coarser than the inverse of the bottom quark mass. Now, we can set up the calculation as initial value problem. We could define the quark propagator, and the quark propagator then satisfies essentially initial value evolution, which I've written here. And of course, there are different pieces of non-relativistic Hamiltonian in this evolution. So that's a discretized evolution. The H naught is a free Hamiltonian, as delta H includes all the higher order pieces, order V to the 4 and V to the 6, spin-dependent parts, so that our action is, or our Hamiltonian is accurate up to V to the 6 spin-dependent part and complete V to the 4th. And that was kind of the explicit form of this on the lattice are specified in this paper by Mino. Of course, we also have to keep in mind that because we integrate the heavy quark mass, we define the energy levels which are related to the actual physical masses to up to a lattice spacing dependent constant, which we need to fix. And in the figures that I will show in this talk, I always used the average mass of epsilon 1s and eta b1s. So the spin average mass as a calibration of all the energy levels. In the lattice calculation, the light degrees of freedom are represented by the gauge configuration obtained from NRQCD collaboration with a physical strange quark mass, up and down quark masses, which are almost as a physical value. In the continuum limits, they correspond to the pion mass of 161 MeV, and we used 48 cube times 12 lattices through the calculation, which give you the transition temperature at 159 MeV, and we vary the temperature by varying beta in order to satisfy this condition that the inverse lattice spacing should be smaller than twice the quark mass, or the quark mass around that range. We only consider temperature from 140 up to 334 MeV. We have to construct now the Meson correlation function out of the quark correlation function. And of course, for that, we need to specify what type of Meson correlation function or what operators we want to use to create those BB bar mesons. So there are several types of operators that have been used in the literature. So we could use point operator, where we put the quark and anti-quark fields at the same point. And that has been widely used by in different papers. And I will briefly discuss those. Now the gamma matrix that enters this operator fixes a quantum number of the state, and in the table I give the operators that have been used to study the corresponding state. We could use something more sophisticated, which more resembles a physical meson, where we displace the quark and anti-quark fields by some distance r, so that what I would call the extended operator. So we take the same correlation function, but replace the operator OP with the extended operator O, and of course this the displacement is weighted by the corresponding wave function, and you could choose something like a Gaussian wave function or more realistic wave function, actually from potential models. What I will mostly discuss today will be the optimized correlator. We actually use several extended Meson operators with realistic wave function from a Cornell model, and then form orthogonal combinations of those, as I will discuss in the next slide. And those are operators which I denote by alpha tilde. And then, of course, because they're orthonormal, if you take different indexes alpha and beta, you get 0. So you essentially get only diagonal correlation in this case. Now, I also want to consider a mixed correlator, which are then closely related to Bethe-Salpeter amplitudes. And that's when I take an optimized operator to create a bottomonium state O tilde, and then correlate it with a point split current, where I displace the quark and anti-quark by fixed distance r. Now, at large times, this operator decays exponentially with the ground of the energy of a given bottomonium state, and the prefactor is what we call the Bethe-Salpeter amplitude. In the non-relativistic limit, then actually corresponds to the wave function. So now here is the optimized operator that we construct. So we use the wave function psi I r capital from the Cornell model, taking down discretization effects on the lattice, construct the wave functions, solving a Schrödinger equation, which is shown in these figures, and then form the orthogonal, form the corresponding linear combination by solving the generalized eigenvalue problem. Originally, the correlation function between OI and OJ are non-zero for different IJ, because none of these operators have a perfect overlap. But after orthogonalization procedure, you get something which is essentially diagonal. And then, of course, you have to determine these eigenvalues and the corresponding rotation matrix. Now, first, let's discuss the point operators, which have been used so far in the literature for several years. And in order to analyze this operator, as customary in the lattice calculation, we introduce the concept of effective mass, where we take the correlation function to neighboring time classes and a logarithm of that gives us the effective mass, so the effective exponential rate at time t. And what you see is that, in fact, you expect that this effective mass should plateau to the true ground state mass or the ground state energy of the state at large enough time. But in fact, if you use point correlators, that doesn't happen for time smaller than 1.2 Fermi. If you use a smeared operators, so where you use more realistic wave function, actually you could achieve a plateau in the effective mass for distances considerably smaller than 1 Fermi. Now, if you look at the corresponding effective masses calculated finite temperature, what you see is that there is not much temperature variation. So in fact, you can go to the highest temperature and you barely see any change in the exponential decay of the correlation function, which of course looks strange. However, you have to realize that of course the short distance behavior of the correlation function is related to can be described in principle in perturbation theory. So the high energy part of the spectral function, which is describable by perturbation theory, is not encoding the Meson physics, essentially dominates the correlation function, and therefore you have very little temperature dependence. In fact, for chi B0 states, I show the lines, and the line represent effectively a naive expectation of what the short distance behavior should look like of the correlation function if you just assume just a plain continuum in the spectral function, no bound states, and that seems to describe the data quite well, at least at the highest temperature. You don't expect perfect description because those lattice data, and we don't correct for lattice in this calculation. Now, we could go to the optimized correlation function at 0 temperature first, and just look at the effective masses as functions of tau. And you see that for the ground state, we get a very nice plateau starting at very short distances of order 0.2 Fermi. We also get a nice plateau for 2s. Again, at short distances, much smaller than 1 Fermi, and the 3s. So actually, this diagonalization procedure works very well for 2s states, projecting out the corresponding ground state masses. And it actually also works for chi B0 1p and chi B0 2p states. So for all quarkonium states or bottomonium states below the threshold, it works nicely. Of course, there is still some residual part which comes from the high energy part of the spectral function. So if we want to parameterize our spectral function, we could think of it as consisting of a rho medium, a low energy part, which can be influenced by the medium, and that encodes all the bound state physics, and the high energy part, which to the first approximation is given by perturbation theory, although the explicit form of that part is not essential. If at 0 temperature, of course, we know we have well-defined Meson states, so the medium part is just sum of the delta functions, or one delta function in this case, because they project on different states. So what we expect is that the 0 temperature correlator should be given by an exponential decay plus some high energy part, which of course is unspecified. However, because we have a nice exponential decay that can be clearly seen, we could determine the constant A and the mass of the bottomonium state from the fits of the correlator, and that also determines then if you subtract those from the correlator, that gives you a parameterization of the high energy part of the correlator. Now that will be important in the next slide. But let me, before moving further, just show that actually the medium effects is not sensitive to the choice of the correlation function. So here I show the effective masses of 2 different correlation functions. One obtained with Gaussian extended operator, So sort of realistic, but not the optimal choice. And then the optimized correlators, the blue circles, and you see that within the errors, you see no significant difference in the behavior as function of tau in these effective masses. So now what we do next, we subtract the uninteresting high energy part from the correlator. So we introduce a subtractive correlator, which the finite temperature correlator minus the high energy part, which is perceived to be temperature independent, and calculate the corresponding effective masses for the subtracted correlator. And this is shown in these two figures for the 1s, 2s, and 3s epsilon state, as well as for chi b 0, 1p, and chi b 0, 2p states. And what you immediately see is that maybe for 1s epsilon, you could identify something that might be a plateau, but even there you see a slight tilt. But clearly for higher excited state, they don't reach a plateau. They show first a linear decrease and then a much steeper decrease at very large time. And the same is for P waves. Now this increase, one could understand with the effect of thermal widths. In fact, if you would assume that the spectral function is a broadened peak, and simplest parameterization would be a Gaussian, and for Gaussian parameterization actually would exactly have a linear decrease in the effective masses. It's very easy to see. Of course, it's not exactly Gaussian. It has some complicated shape, or could have some complicated shape, especially at low omega. So to parameterize the complication of the shape at omega, which are away from the peak, we introduce additional fit term. That's this delta function. So it's just a delta fit at much smaller frequencies, so well below the peak, and with some corresponding amplitude. But the physics information is actually encoded in this Gaussian form of the spectral function in terms of as temperature-dependent widths and a temperature-dependent mass. So the idea is then to use these two parameters and to see if you could fit the data, and actually you could fit the data very well because the data already tells you that you have this approximately linear behavior. So the lines shown in these figures are the fit to this ansatz of the spectral function, and from the fits we determine the temperature-dependent mass and the temperature-dependent widths. So here I summarize the results for the temperature-dependent widths, and you see that the widths of different epsilon state increases with increases temperature, kind of seemingly linearly. And the width of higher excited states is bigger. So if you go from 1s states to 2s to 3s, there is a clear increase in the width. In fact, for the 3s at the highest temperatures, the width is bigger than the difference in the energy level, so in the level spacing between different states. So at this moment, speaking about 3s states is not very meaningful. The same thing you could you find for also for chi b 0 and chi b 0 1p and chi b 0 2p states. Again, the width of chi b 0 1p states is larger than the 1s, but is smaller than the 2p state. So roughly the thermal width follows the hierarchy of the size as you would expect. We also calculated the masses, and we present the result in terms of effective mass shift. So the masses in the medium minus the mass in the vacuum. And here, to somewhat surprisingly, we see almost zero effect with errors of the calculation. So in other words, we have no indication that there is a statistically significant shift in bottomonium mass for any of the states below the threshold. Okay, so now the last two slides, let me discuss the Bottomonium Bethe-Salpeter amplitude. And as I said, we consider this mixed correlation function where we correlate the optimized operator with a point split Meson operator at distance r. So here we have, in addition to the time dependence, this index r, which essentially measures or studies the correlation function as the separation between quark and anti-quark. Now, if you do a spectral decomposition of this correlation function by inserting a complete set of energy eigenvalues, a complete set of states, and you go to large time, because you use the optimized operator, essentially you're left with a single exponential decay for given state alpha, or a given quarkonium state alpha. Now with an operator that depends on index R, and in the non-relativistic limit, this is well, that essentially that is overlap of a given state with a configuration that is created from the vacuum by having a quark and anti-quark at distance R. And that's what is called the Bethe-Salpeter amplitude, and in the non-relativistic limit that reduces to the wave function. So we could assume that this quantity phi alpha is satisfies the non-relativistic Schrödinger equation with some potential. So if you have the energy values alpha from the lattice, and you determine the Bethe-Salpeter amplitude using the Bau equation from the lattice data, in principle you have phi alpha for 3 states, 3 epsilon states. You could easily determine the mass and the potential and have additional constraint for consistency. And when we play this exercise, and it turns out that the potential agrees very well with the standard Cornell parameterization, as well as the lattice calculation of the potential from Wilson loops at some small lattice spacing. So all these 3 states point to the same potential, and you could also determine the constituent mass entering this equation to be 5.5 GeV with a 300 MeV error. Furthermore, if you have the mass and you know the potential, so if you fix the potential to be either the lattice or the Cornell potential, doesn't matter, they are the same, you could try to reproduce or you can actually calculate the Bethe-Salpeter wave function from potential model and compare to the lattice results. So the open symbols are the potential model calculations, the filled symbols are the lattice results, and you see, well, there is no perfect agreement, but certainly you get pretty close to the description of the lattice data. So in other words, this potential model can be justified by directly calculating the Bethe-Salpeter amplitude at 0 temperature, and the potential model seems to capture reasonably well the corresponding wave functions. Now we could calculate the same correlation function at finite temperature. Now there are 2 ways you could use it. Of course, you could say that it's just another correlation function that will be affected by the medium. So you again look at the effective masses of the corresponding correlation function, and here I show the epsilon 3s effective mass for 2 different separations, R 0.25 Fermi and R 0.65 Fermi on the right. And you see that at high temperature, you see again the same feature, that the effective mass decreases linearly, and as I argued, that could be understood as effect of the thermal width. And the thermal width apparently becomes larger when you use a larger source. So again, that tells you that if you have a configuration of quark anti-quark, which are further apart, that's more likely to dissociate. But qualitatively, the effective mass shows similar thermal effects to the one we get from the optimized correlation function. You could also calculate the corresponding Bethe-Salpeter amplitudes, and surprisingly, they do not show much temperature dependence. Certainly, you see some temperature effects, but the effects are small. You see, in effect, the fact that you see some temperature dependence, and unlike in the 0 temperature case where you could vary your time variable to be anything, and the results are independent of the time variable, here you see some dependence on the time variable depending which value of time you choose. But overall, the structure is the same as at 0 temperature, or pretty close. And therefore, this picture where you would assume that you have a screen potential and somehow the wave function strongly modifies, the state becomes less compact, that potential picture with screen potential seems to be disfavored by this lattice calculation of the Bethe-Salpeter amplitude. Okay, so that brings me to the summary. I tried to explain that there are several operators that you could use to study the correlation function, and point Meson operators that have been used in the past to study Bottomonium and NRQCD have poor projection. to the ground state and therefore not very sensitive to thermal effects. So using those operators is hard to constrain in medium properties of bottomonium. On the other hand, correlation function of extended operator or combination of those extended operators, which leads to optimized correlation functions, they very much sensitive to the thermal effects and point to the existence of thermal widths. Using a simple ansatz for the spectral function, we extracted the thermal widths of all bottomonium states below the threshold and found that the thermal width increases with the temperature and follows a hierarchy of the bottomonium sizes as expected. However, we didn't find significant thermal modification of bottomonium masses in contrast to expectation with potential models based on screen potential. And we also studied Bethe-Salpeter amplitudes that confirms the potential picture of bottomonium at 0 temperature, but doesn't support the potential picture with screen potential at high temperature. So that's all from my part. Thank you very much for your attention.
Thank you. Thank you a lot, Peter. Let me see. Are there any questions? Hi, Tao, please go ahead.
Yes. First, thank you for a very nice talk. So I have a question about the effective mass. So when you were analyzing the effective mass, you once tried to remove, subtract the contribution from the high frequency part. I'm curious how you determine the contribution from this part.
Well, so here the essential point is that you see you get a ground state, or not necessarily the ground state, but you get a state of interest, so whether it's 1s, 2s, and 3s from these operators, and something else at high frequency, because the effective masses certainly not reach, won't go to a plateau, right? So they increase at large, at small time, which means that you have some extra contribution and you don't know what it is. So what we say is that the spectral function is the sum of a delta function, which parameterize a bottomonium state of interest, and some high frequency part, which you could parameterize somehow, but we don't do it. Instead, having this ansatz, we get the correlation function written as an exponential decay plus something else. And if I use the lattice data only at large enough distances where this part is dominating, so I could always at 0 temperature fit with single exponential decay, right? From effective mass, you see you have a nice plateau, so it's just given by 1 exponential. From that large tau behavior determines a constant A alpha and M alpha. And once I know them, determine them at 0 temperature, I subtract that part, this exponential decay, from the correlation function, left with the rest, which is the C high. And this C high, because it's a high frequency part, is assumed to be independent of the temperature, so then I could subtract it. So I subtract something that I determined at 0 temperature where I have this luxury of having a tau range where it's everything dominated by single exponential. Mm-hmm. And then that gets subtracted from the finite temperature. Okay. So you could say that this extra information comes from the 0 temperature calculation, and that for each lattice spacing, for each temperature that I show, I have the corresponding vacuum of 0 temperature calculation, so I could do this subtraction.
Mm-hmm. Okay, thank you very much.
Okay, next question, Petrov.
Could you explain in simple terms why masses do not depend on the temperature, while the weights as the lifetimes they do?
Well, I don't have first of all, of course, you don't know. If you believe the naive picture of Matsui's Zatz, you would say, well, the potential gets modified in the medium, and therefore, of course, you would expect some shift in the mass, right? If you have a different potential in the medium, the binding energy is different, so the masses of bottomonium states will shift. However, this picture assumes that the time scale of the medium is pretty fast, so it's much smaller than intrinsic time scale. So in some sense, you could integrate out the time scale related to the medium, and then of course the potential is modified. Now, if you assume a different hierarchy of scale, where you say that, well, the bottomonium is a small object, right, and the orbital time of bottom quark inside bottomonium is small, they don't really see the medium in a usual way, right? So the interaction with each other is not modified by the medium to the first approximation. So the potential is temperature independent, and you just have business as usual. However, they could still interact on a longer time scale with gluons surrounding by the medium, which it will increase the thermal weight. So I guess in a picture where you assume that the time scale of bottomonium is much smaller than the medium time scale, actually it is natural, but of course you don't know if that's a good approximation. And of course, it just, after the calculation, it seems like the lattice calculation favors this picture where you don't see a modification of the potential.
Could it be related maybe to time and to temperature dependence of the imaginary part of the effective potential? No.
Well, in a sense, yes. But again, I mean, of course, you always have. I mean, you always could say that the mass, the pole position, right, is imaginary because it has a thermal width. So that's always. But that is imaginary part of the potential. That of course relies on the fact that, again, the time scale where you dissociate somehow the bottomonium, or at least the binding potential between them, is much shorter. So it's kind of resumming the effect of dissipation into a potential. But you could also have an imaginary, or the thermal width, without having imaginary potential. So you would always have a thermal width, I would argue, independent whether you have an imaginary part or not. The imaginary part, of course, is when to some extent you have a lot of rescattering of this Coulomb gluon inside the bound state with a medium, and this Coulomb field gets destroyed, kind of a short time scale. So that's one possibility, but not the only one.
Okay, thank you. Thank you.
Okay, thanks a lot, Peter, once again. And let's move on to the next speaker.